Okay, so let me introduce Nathan. He joined the Quantum Device Lab in ATH in Zurich in 2019, and his work focuses on variational quantum algorithms for combinatorial optimization and on quantum software development. And he will talk about the continuous gate sets for variational quantum algorithms. So please go ahead.
Okay, great. Can you all see my screen?
Yes.
Okay, great. Perfect. Thank you. So thank you very much for the introduction. And I'm really happy to be here and represent the Quantum Device Lab from ETH Zurich, led by Andreas Wallraff, and also our collaborators, Augustin Di Paolo and Alexandre Blais from the University of Sherbrooke. And I will be speaking about, maybe I will change my pointer. I will be speaking about the recent research results that we've had on quantum optimization algorithms, namely where we have looked into improving the performance of those quantum optimization algorithms using superconducting qubits that you see here on the front page. So we have a 7-qubit quantum processor. And with continuous gate sets, which will become a bit clear in the rest of the presentation, we've tried to improve the performance of this algorithm. So all the details are also in the paper that is now on the archive, so feel free to also give it a read. And because our research focuses on an application that relates to near-term quantum computing, I will briefly start by giving sort of an overview that probably most of you already are aware of about near-term quantum computing. So the quest for fault-tolerant quantum computing is continuing. We're not yet there, but we're progressing. And maybe one interesting point is that in the meanwhile, there has been a significant interest in the last years to develop applications for near-term quantum computers. And this is challenging. I think it's interesting both for companies and research labs. And you can also really see that into who is actually developing those applications. You can really see that it also interests companies. So I think this talk is also a great fit for the setting that we're in right now. Obviously, there are a lot of challenges in developing those near-term applications. And the two main ones are firstly that we have a low number of qubits. Right now, we sit around 50, or Google and IBM have 50 qubits. This is for superconducting circuits at least. And it's progressing, but not everyone is there yet. And we know that in the near future, we won't have access to millions of qubits. The second challenge relates to the limited number of operations that we can have in a quantum circuit. So both theorists and experimentalists also hope that we would have an infinite number of operations, that you could just run those computers indefinitely, but unfortunately that's not the case. And where to give maybe an indication of where we're at right now, like the best performance, if you look at 2-qubit gates, the time that they require, and divide this by the qubit lifetime, we're around for the best quantum processors around a factor of 1,000, meaning that we could do in principle up to 1,000 2-qubit gates within the lifetime of the qubit. But this is obviously in the best case scenario. And in this talk, we'll mostly focus on this second challenge and try to come up with ways of improving the performance of algorithms that require a lot of operations without changing the hardware, but rather by just looking at what operations are performed and change that. So to get a better understanding of what I mean by that, let's first look in a very high-level way of how quantum circuits are generated to solve problems on quantum computer. So we start with a problem, which is then formulated in terms of an objective function and some constraint, and this is given as input to a quantum algorithm. The quantum algorithm spits out some steps to follow, And those steps are then passed on to the quantum computer. And unfortunately, that's not the last step. So there's an additional step of checking what the quantum computer can actually do in terms of operation. And this is usually, there's a few gates that are usually used because we know that by using these gates, sorry?
Please mute your, someone is not muted, I think.
Yes, I will then just continue.
Could you mute everyone?
Yes, done.
Yeah. Sorry.
Okay, no problem. So by using those standard gate sets, we can decompose any of those steps that are spit out by the quantum algorithm and create a gate sequence, which is then this quantum circuit that we will run on our quantum computer. But unfortunately, it can get a lot longer because the decomposition using those standard gates is not always efficient in terms of the number of operations that have to be performed. So one way to reduce the total number of operations in the quantum circuit is actually to look exactly at that and change the gate set and replace it by a tailored gate set that will then depend somewhat on the quantum algorithm that is passed in or that we use. But by changing the type of operations that we perform, we can reduce the length of the gate sequence and therefore solve more complex problems with the same hardware. So in this talk, I will try to show you what we have done, and we have focused on the quantum optimization algorithm, but other labs have also, especially companies actually have looked into similar ideas of using tailored gate sets or continuous gate sets to perform these in these quantum circuits and less operations. There's Google that started in 2015, and then this was for quantum simulations. Then IBM also did it for quantum chemistry. Rigetti also did it for QAOA, but for specific type of mixers. And then Google again showed a new way of doing that with their new gates. So let's dive right into it. So I will first explain you a bit of how the quantum approximate optimization algorithm works for those that don't know what it is. The quantum approximate optimization algorithm, often called also QAOA, is a hybrid quantum classical algorithm, meaning that the workload is shared by both the quantum computer and a classical computer. Essentially, a parametrized state is prepared on the quantum computer, and thereafter a classical optimizer is used to optimize a parameter, so on a classical computer. And the idea of QAOA is to find approximate solutions to combinatorial problem. And before you even start to do QAOA, what is important is that your problem can be mapped to an input that QAOA can use, and in that case, it is usually a Ising Hamiltonian. This is at least the straightforward and most well-known variant of QAOA, where a computational problem is mapped onto an Ising Hamiltonian, of which the ground state is the solution to the original problem. And then once we have that, we can use the QAOA protocol, and it consists of 4 main steps. The first one is to initialize all the qubits into a uniform superposition over all states, and then prepare NAND states that consist of P layers. So here, each one of these blocks is one layer, and there's P layers, each of which consists of 2 unitaries. The first one, called the cos unitary, is related in some form to the problem Hamiltonian. And the second part is called the mixing unitary. And this one is essentially just single qubit gates in another basis than the problem Hamiltonian. So for our talk, or this talk that I'm giving here, will mostly focus on the first one. Then once we have this prepared state, we can measure it in the Z basis. So that's the third step. And using the repeated measurements, we can evaluate on a classical computer the expectation value of C in this specific state, and thereby also update the variational parameters. So there's 2 for each layer and 1 for each, essentially 1 for each unitary. And we can update that until the prepared state converges to the ground state of the system. So one last point that is of importance here is that the performance of the algorithm depends on the number of layers. It's not entirely clear yet. It's still an open question onto how it depends on the number of qubits, on the number of terms in the problem Hamiltonian. This is not clear, but we do observe that the performance of QAOA clearly depends on the number of layers that are used for this, for the implementation. Okay, so now that we know a bit more about the algorithm, we'll get into the gate sequence specifics and try to understand how we can make use of a continuous gate set in this setting and why it's useful. So I will focus again on this cost unitary, because this is the part where we have the 2 qubit gates that relate essentially to these terms in this first sum here, where the Z is a poly operator, and where the J is essentially the coupling that depends then on the mapping of your problem. And in this unitary, all terms in C commute because they're all in the Z basis, and so each term can be considered separately. So for the sake of simplicity, we'll just be looking at one term between qubit I and qubit J. And to implement this unitary, the one thing to realize is that it is essentially a phase factor that depends on 2 variables. In this 2 qubit subspace, it is a phase factor that depends on 2 variables. Firstly, your problem Hamiltonian, and also the variational parameter. And since the variational parameter can be any real number, this phase factor is really an arbitrary phase. And therefore, when you try to implement this unitary using the standard gates that can only do, so I don't know if you're familiar with them, but for instance, the CZ gate is a conditional pi phase gate, meaning that it can add a phase of pi on the 1-1 state in this 2 qubit subspace. And if you try to implement an arbitrary rotation, you're obliged to somehow decompose this unitary that we have here into 2 qubit gates, two 2 qubit gates, and then some additional single qubit gates. And the arbitrary rotation is introduced by this single qubit gate here. Now, if on the other hand, you are able to make a 2 qubit gate that can directly implement this rotation, this arbitrary rotation, then you need only one of those 2 qubit gates and then some additional single qubit gates. So there's less operations, and it will obviously also take less time. The second part of the layer, which relates to the other unitary, stays unchanged for both methods. So then we take this and we repeat it p times, and then we get the total gate sequence that we run on our quantum computer. So now that we know which gates we want to make in practice, how do we implement them physically on our quantum computer? So we're using, at the Quantum Device Lab, we're using transmon qubits, which are a bit like artificial atoms. And we simply make the single qubit gates by sending microwave pulses on a two-level system. You can picture it as a 2-level system, and thereby we can move each qubit individually on its own block sphere. Now, to implement 2 qubit gates that relate to QAOA, so the gates that add phase on the 1-1 state, we make use of an additional state of the qubit, which is the 2nd level excitation. So this one we obviously don't want to use it's also the computational basis, but we can still use it to make our 2 qubit gates. And this is a relatively common approach. When you hybridize 2 qubits, you get essentially this level diagram. And for now, we'll focus mostly on the 2, 0 and the 1, 1 state, because those are the two states that matter. This is the state on which we want to add the phase, and this is the state with which we will interact. So what happens is that we move the 1, 1 state in resonance with this non-computational state. And so this is what we do here on the quantum computer. What you essentially see here is that with a flux pulse, we move this 1, 1 state up to resonance with the 2, 0 state, and this we indicate on this axis by the detuning between the 1, 1 and 2, 0 state, which is, so at 0 detuning, which is what you have right now, this on this picture, we're at this stage essentially. And what happens then is that you, if you wait for the right amount of time, you will have a population exchange, so a coherent population exchange between those two levels. And after one full oscillation, all the population will be back into the 1, 1 state with an added phase shift of pi on the 1, 1 state. So this is exactly what we want to do as CZ gate. And this is well known, but now what we have done in this case is that we've extended this scheme to being able to measure any or to add any phase that is between 0 and 2 pi. And to do this, we have to adapt the time, because the length of this oscillation period depends on the detuning, and therefore we have to make sure that we get all the population back into the 1, 1 state, which is here illustrated by all those dots that are sitting on the white line, which is when all the population is back into the 1, 1 state. And by essentially choosing the right set of parameters, we can then implement this whole function and implement an arbitrary phase. So this is the concept behind the arbitrary phase gate, that we need to implement what we call the direct implementation of the arbitrary phase gate. So now that we know which gate we can use or which gates are required, let's try to just pick problem instances to compare the two approaches on a quantum processor. So this is the processor that we've been using, and for now we'll just look at an abstract representation of it, where edges or where the qubits are the vertices, and the edges represent the qubits that are physically connected, thereby enabling a 2-qubit gates without any additional swap gate. And in our case, we decide to use the exact cover problem, that is an NP-complete decision problem that is nicely visualized in this type of matrix here. So in the first case that I'm showing here, we're looking only at a subset of qubits that is here circled by this gray dashed line. And the idea of the problem, so the solution that what we're trying to solve is to understand or decide whether there exists a combination of columns such that each row of this matrix is included exactly once. So in the first case here, it would be, for instance, if I select column A1 and A2, together I cover each of the 3 rows exactly once. And if on the other hand, I select the B2 column, I also cover all the rows exactly once. And the columns that you see here are each mapped to a qubit. And to know whether in the solution we decide to include a qubit, or in other words, a column to the solution, we change the bit value to 1, meaning that if we want to find solution to this problem here, it means that we would have to measure qubit 1, qubit so qubit A1, qubit A2, and then 0 on qubit B2, such that this whole state that we measure there is one of the first solution that I spoke about. The other solution would then be the 001, which would correspond to selecting only the last column. And so this is, thankfully, this type of computational problem can be mapped to a Ising Hamiltonian, which you see here. And those are the solutions that I was speaking about. Now, this is the example that we'll use in the presentation to understand and get an intuition for what's happening. And then once we get the good intuition, we'll also discuss this 7-qubit instance that also has 2 solutions, so the first 4 column and the last 3 columns, to see how it performs on larger scale problems. So we start by doing a QAOA implementation with only 1 layer. So you remember I was saying that the performance depends on the number of layers. This is true, and therefore 1 layer won't be the best won't perform best. But on the other hand, there's only 2 variational parameters. So the advantage of that is that we can map out the entire cost function, which is this expectation value of C depending on the in the state that is parameterized by gamma and beta. And since there's only 1 gamma and 1 beta, we can map out the entire parameter space. And this is what you see here, the measurement from our quantum computer. So there's 1 global minimum right here and 2 local minimum right there. And so when we look at that, we see that it corresponds quite well to a noiseless simulation that you see here. And the other part that is important to verify is whether this landscape or this optimization landscape can be used for optimization, as in the QAOA scheme where we use this classical computer. And to this effect, we start with random initialization of betas and gammas, and we simply use this cost function into a classical optimizer. In our case, we just use an LDME optimizer to evolve the parameters. And here you see the convergence traces of the gamma parameter on this plot and of the beta parameter on this plot. And when you do that, you see that most of those parameters converge, the pairs of parameters converge to this global minimum right here. And a few of them get trapped in some of the local minimum. But it shows that the landscape is suitable for optimization. And here you see the energy or the cost function as function of iterations. One thing to point out, though, is that even in a noise-free simulation, we do not reach, or the cost does not reach the ground state energy, because for the problem instance that we're considering here, which is this 3-qubit case, the ground state energy is minus 1.5, and you see that even here in the best case, we're not getting a lot below -1. So in order to cope with that, we introduce some more layers. But when there are more layers, we cannot map out the full parameter space. And therefore, what we do is that we look at the output probability distribution, and also to distinguish between the classical optimizer that might have some issues finding the global optimum. What we do is that we first optimize all the parameters on a classical computer using the noise-free simulation, and then we initialize a quantum computer with those values. So we initialize the parameters with the optimal that we found in simulation. And then we perform a few more iterations just to make sure that we reach the local minimum in that area of the parameter space. And so when we do that, so this is what we would measure for 1 layers. And maybe I'll take a bit of time to explain what we're seeing here. So you're seeing the measurement outcomes, the probability of measuring each one of those states. And what is measured is everything that is filled with a color. And those that are blue correspond to the solution of the problem that we have here in the right-hand side. So we see that with one layer, we have some probability of measuring it, but it's also not unit probability. To compare this to simulations, we do 2 types of simulations. First, noise-free simulations, which are here the black wireframes, and master equation simulation that take into account so T1 and T2, and also the residual ZZ coupling between the qubits. And we see that it matches quite well what we measure. So then we also add some additional layers, and we see that when we're using this arbitrary phase gates, really the success probability or the probability of measuring one of the two solution states increases both in the measurement and in theory as expected. So this is obviously what we want. And after 3 layers, we have essentially reached unit probability in theory, or at least in noise-free simulation. And we're not that far from it using this direct implementation of the arbitrary phase gate. If we compare this to using the other method that we talked about, so the decomposed implementation of the arbitrary phase gate, there we do see that there's a bit more discrepancy, or rather that the measurements are slightly more different from the noise-free simulation. And this is mostly because of decoherence, mainly because we see that the simulations, the master equation simulation, fit quite well with our data. And in this case, the fact of adding additional layers is not always beneficial, because you just also add more noise. And therefore, in practice, the total probability of measuring one of the solution states decreases. But here you could argue that there's only 8 states to pick from, and that also 2 of them are solution states. So essentially, even if I was picking from a uniform distribution, I would have a 25% chance of measuring one of the correct states. And so we look at another metric that we call the enhancement, which is essentially how much better are we doing with this probability distribution that comes out of QAOA compared to a uniform distribution of all states. And this becomes also this will become also more meaningful as we look to a larger problem where there's also more states. So here we plot the enhancement as a function of depth, so as a function of the number of layers in the QAOA algorithm for this 3-qubit problem that we were also discussing right before. So here you see the QAOA depth. So we go up to 9, I believe, in both the direct implementation in blue and in green, the decomposed implementation. And here for reference, we also show the sequence duration in microseconds, so how long it takes us to implement those sequences. And for reference, we also show the enhancement of the noise-free simulation. So just to clarify, this enhancement, as I said, is the success probability, so the probability of measuring a solution state divided by the probability of finding an answer from a uniform distribution. And the main point that I want to bring across these 2 of them, firstly, that there is a trade-off between additional layers that, in theory, increase the probability of measuring one of the 2 solution states, or one of the solution states, but in the experiment also result in longer gate sequence, and therefore more noise and more errors, and therefore, in the end, a lower enhancement and lower success probability. And the main point that I want to make relates to the fact that if we use this direct implementation, we can implement more layers for a fixed sequence duration time. So for example, if you look at 1 microsecond here, which corresponds to 3 layers with a direct implementation, with the same amount of time, if we use the decomposed implementation, we can only use 1 layer. And in that case, you see that it will make a big difference for problems that require a lot of layers to be solved with high success probability. And this is also what we see when we switch to this 7-qubit instance, where essentially the number of layers that are required to reach a high enhancement and a unit success probability is more than, so here is more than 6, meaning that clearly if we use this direct implementation, we will manage to, we will be able to harness these additional layers more effectively than if we use the decomposed implementation. And using that, we see that the direct implementation on this 7-qubit problem instance achieves 3 times higher enhancement, thanks to the fact that for that we can just implement those sequences in a shorter amount of time. And we see that we are in fact coherence limited because for instance, or there's some indication at least that this is the case, because if you look at the direct implementation after 5 microseconds, we're roughly at the same performance as 2 layers of the decomposed implementation that is of the same sequence duration. So this really shows that we're limited by the sequence duration for those complex problem instances. So this brings me to my conclusion. And so we talked about those arbitrary phase gates and more generally speaking, continuous gate sets that can enable efficient decomposition for variational quantum algorithms. And we have illustrated this on the QAOA algorithm. We have then also solved 2 exact cover problem instances requiring deep QAOA implementation, and seen that by using the direct implementation, we can achieve higher enhancements and higher success probability. And finally, I would like to conclude with the fact that we expect this advantage to increase further as we progress towards larger experiments, because involving also more qubits, because the number of gates that we save actually also scales with the number of qubits, for instance, that cannot be, or the number of terms in the problem Hamiltonians, and therefore also usually the number of qubits in the experiment. So that's it. Thank you very much, and I will be open to any of your questions.
Thanks, Nathan, for this nice presentation. I'm sorry that we are running out of time, so let me just ask you one of the questions of the chat. There are much more questions there, so if you don't mind, you and Maria to stay longer this official seminar, we will just continue the discussions later. So let me just ask you the first question that raised Pierre-Luc. How many bits of precision do you have of the parameterized control Z rotations?
Can you repeat that question? I'm not sure I heard it correctly.
How many bits of precisions do you have on the parameterized control Z rotations?
Okay, so this then relates to the precision. Well, what we see is that maybe I will go back to this point here. So we don't really characterize it in terms of bits of precision, but what we can tell is that we have investigated, we do make some interpolation errors, because what we do is that we interpolate those all the parameters linearly or between 2 calibration points. And we do see that indeed there is a, as we measure less and less calibration points, we make larger and larger errors. What we have seen though is that those errors are not significantly larger than what we have when we have a single point, because they're also with fluctuating frequencies in time. So our gates slightly drifts out of its calibration, and we're in the same area of errors, which is usually 1 or 2, between 1 and 2 degrees of conditional phase. So plus or minus 1 degrees of conditional phase. So this is roughly the precision that we have, and it doesn't really matter how many points we have. This interpolation is good enough.
Okay, thank you. So thank you, everyone. We should stop the QRST here because we're running out of time, but please stay longer if you want to continue the discussion with the speakers. And there were very nice presentations, both Maria and Nathan, so thank you very much for your contributions. And looking forward to see you all to the next QRST.